My name is Keith Wells and I'm a mechanical engineering student at USQ. This is my video explanation of my MEC2406 Assignment 2 project. The design of my plant included two DC motors mounted at the extremities of the seesaw beam to provide the greatest moment for the rotational force. I mounted the gyroscope along the pivot point. It could have been mounted anywhere, however the center pivot point had the least amount of vibration. One of the biggest challenges for me in this project was managing the angle drift from the gyroscope. To manage this issue, I regularly monitored the gyro angle drift using a serial plotter. The y-axis of the graph shows the angle and the x-axis represents each time a print command is executed, which is a function of time. The set point is shown in orange and the angle recorded by the gyro is blue. Here we can see that the angle of the plant is not moving. However, the gyro drift is. I was able to manage this issue, however I was not able to totally eliminate the drift, and this did have a slight impact on my test results. To tune the PID control system, I used the Ziegler-Nichols tuning method. Initially, I had some difficulty tuning the system, which required me to perform some troubleshooting on my project. The first problem I encountered was that the system was slow to respond on one side. I printed the input PWM signal to both motors and the output value from the PID equations to the serial plotter oscilloscope. The graph shows motor 1 in blue, motor 2 in red, and the output from the PID equations is in green. I could see from the graph that the motor base speed was indeed set to 128. The output signal to each motor was reflected along the base motor speed axis, and the output signal was accurately added to motor 1's base speed and subtracted from motor 2's. The graph confirmed that both motors were indeed receiving the correct PWM signals and allowed me to diagnose the lazy motor. When tuning the PID gains, I had a little difficulty determining the KP at which sustained oscillation occurred. To overcome this, I printed the angle data to a serial plotter which allowed the point at which sustained oscillation occurred to be easily found. I then measured the period between these oscillations using a stopwatch, and used these values in the Ziegler-Nichols equations to determine my Kp, Ki, and Kd gains. My target when tuning was to achieve a slightly underdamped system response because the testing would need to occur over a relatively short period of time. The response I achieved is shown on the graph. The orange line is the set point, and the blue line is the angle from the gyro. I had a little time left at the end of the assignment, so I added an if-else control structure to my code that allowed me to more accurately calculate the time at which local maximums occurred in the gyro angle data. Test 1 required the system to move to a fixed angle to the ground on startup. Hold this position for 10 seconds, and then move to an angle of -5 degrees. The orange line represents the angle's set point, and the blue line is the angle value recorded by the gyroscope. On startup, the inertia of the motors caused a slight rotation of the system. The code was able to vary the PWM signal to the motors and correct the error caused by the inertia. I experimented with reversing motor directions to try and counterbalance the inertia. However, I was unable to totally eliminate the problem. The system was able to respond almost immediately to the change in the set point. The PID control system was then able to successfully maintain the new angle. Test 2 required the system to move to a fixed angle of 5 degrees at startup. The test also required that the angle of 5 degrees was maintained whilst the base was tilted. The angle starts at 0 degrees and then slightly overshoots the 5-degree target of the set point. The PID control system was successfully able to maintain the set point angle of 5 degrees when the base was tilted. There is some slight overshoot present in both tests because the system was tuned to be slightly underdamped to achieve a good response.